Okay, time to continue. So we have a lecture now by Jacob, and he's going to continue his stream of lectures doing with cluster algebras and their basic properties.
Okay, thank you. So today I want to talk about cluster algebras of surface type. So the reason I want to do this is because remember I said there are two sorts of types of finiteness properties. One of them is called finite type, which means you have a finite number of cluster variables. And one is called finite mutation type, which means you have a finite number of quivers that you get. Okay? So the reason I want to talk about cluster algebras of surface type is, well, I think they're interesting in their own right, but also most cluster algebras that are finite mutation type are of this form. Okay? So most, whatever most means, most finite mutation type cluster algebras come from surfaces. Okay, so before I get into all of the details, all of the formal definitions for these things, I want to redo an example that I did on the first day. The first example, this A2 quiver that I keep doing over and over. Okay? So this is the A2 cluster algebra once again. And now I can say A2 cluster algebra, and you know what that means because it comes from these Lincoln diagrams. I'm specifying the type of the cluster algebra. Okay, so remember when I did this example last time, I took the quiver A2 and I mutated 5 times and I got back to where I started up to relabeling the vertices. Okay? So I want to do this in a different way, where instead of starting with a quiver, I have a pentagon. Okay? So I have some pentagon, and I'm going to triangulate this pentagon, so I'm going to add in diagonals so that I get a triangulation, so that I split the thing into triangles. Okay? So here's such a way to split this pentagon into triangles. And my process of mutation in this case is going to be flipping these diagonals. Okay, so I'm going to perform a flip. I'm going to flip this diagonal. And what that means is, okay, so let me draw the picture. So just as in mutation, it's some local move. Everything kind of far away doesn't change. So this guy, I'm going to leave the same because I'm not flipping him. And then this arc, what a flip means is I find the quadrilateral that this arc is inside. Okay? So it's inside this quadrilateral. And I replace this diagonal with the only other diagonal there is inside that quadrilateral. So I replace this one with this one. Okay? So when I flip this guy, I get this one. Okay? This makes sense. Okay, so this is some elementary thing that you can do. And just like mutation, if I flip this one, I get back to this picture. Okay? So I flip this one, I replace it back to this picture. Okay, so I haven't told you what's happening with the seed yet. I just told you kind of what's happening with the quiver, okay, with the triangulation. So let me add some functions. So I'm going to call this diagonal x1, and I'm going to put an x2 over this one. Okay? So just like when you do mutation, this one stays the same. And then how do I get the function on this one? Let me tell you what you do. Okay? So I take this quadrilateral here, and I'm going to put 1s everywhere along. If it's a boundary, I'm going to put 1s. Okay? So I'm going to redraw this picture. Just this quadrilateral that I'm looking at. And I have x2 here, and then these are 1s, And then this is my red one, x1. And I want to figure out what's going on for this one. I want to know what is this. Right? This is the one I'm concerned with. So there's something called the Ptolemy relation. And this is really sort of classical. Okay? So the Ptolemy relation says that if I inscribe this thing on a circle, so if I put a circle so that it touches all of these vertices, then the lengths are going to satisfy this formula. So let's call this x1 prime, okay, just to give it a name, and I'll solve for this. So it says the product of the diagonals is equal to the sum of the products of the opposite sides. So 1 times 1 plus 1 times x2. And if I solve for my new variable, this should look familiar. This is what we got when we mutated before. Okay? So 1 plus x2 over x1. Okay, so you can continue this process. And the point is this is exactly the same as what we got before. Okay? So if you now the only interesting flip since we flipped this one goes back to here. We have to flip this one. We get the same picture as before. So this guy doesn't change. And I replace this diagonal with the only other one that I can, this one. Okay, and so now just to save time, I think you understand the idea. So I won't write in all the variables, but you do this thing over and over. Okay, so the product of these two diagonals is the sum of the products of the opposite sides. Yeah? Like you want to get a quiver from this. Is that your question? Yeah, so I will tell you in one moment. Yep. Okay. So I keep flipping, and I won't draw the variables, but in every case you have cluster variables on each of these arcs. Okay, and here we're flipping this one. Okay, so this one stays the same. That gets replaced with this. So I flip again, right? So now the only interesting one is this one. Okay. So I get this and this. All right. And now if I, so yeah, this is what I get. And now this one turned into this one, so I should flip here, and what I get is here. Okay? So if I flip this one, I return to where I started. Okay? So this is an example we've seen before. And last time, I just want to note something. Last time when I did this example, remember, like we get back to where we started, but up to relabeling the vertices. So if you follow one of these arcs around, like I take this one, I flip it here, and so on, and I follow that one guy around, then they'll end up being switched. Okay? So the same thing happens. Okay. So let's talk about how to get a quiver from this triangulation, like the question that was asked. Okay, so here's what I'll do. Maybe I'll just take this one, but you can do the same thing for all of these triangulations. So here's the prescription. So for every one of these boundary edges, I'm going to have a frozen vertex, one of the ones that I cannot mutate at. Okay? So frozen vertex. So in general, for every edge, I'm going to put a vertex there, but the type depends on whether you're a boundary or not. Okay? So frozen vertex on boundary edges. And mutable on the other ones. On each, I'll call it diagonal. So there's only 2 in this picture. And how do I get the edges? Well, so this is somewhat artificial. I mean, there are 2 choices, so you make choice whether you want to do a clockwise cycle or a counterclockwise cycle. Okay, so I'll use clockwise in this talk. So you go clockwise. You do a clockwise directed cycle for each triangle in your triangulation. Okay? So let me draw the picture. So I'll draw frozens in blue because they're frozen. Okay? And then just to have some other color, I'll draw the mutable ones in red, okay? And then clockwise is like this. So I'm going to have an arrow here, okay? And every one of these triangles, I go clockwise in a cycle, okay? So I have an arrow here and an arrow going up. Okay, and I do the same thing for all of these cycles. Okay? So this is the quiver I get, and it's an A2 quiver that you've seen before if you forget about all the frozens. Okay? Just this picture in the middle is the A2 quiver. Okay? What's that? Sorry, I can't hear you. You want to be consistent. Just if you choose clockwise, be clockwise for every triangle. And if you choose counterclockwise, be counterclockwise for every triangle. Yep. Okay. So here's an exercise if you want to get some practice on this. I mean, so one nice thing is that this process of going between a triangulation and a quiver, it preserves mutations and flips are doing the same thing. So what I mean is if I take the quiver and mutate at some vertex and then make the triangulation, or flip one of these arcs from the triangulation, then make the quiver, I'll get the same answer. Okay? So I'd like you to try this when you have some time. Okay? So here's a particularly painful one, but you can do a simpler one if you like. Okay? So for A5, I get an octagon. And let's draw some triangulation of the octagon. So okay. So now this is split into a bunch of triangles. Okay? And maybe the first thing to do is, pick any edge that you want, any diagonal that you want to. So maybe pick this one, whatever you want. So flip the diagonal, make the quiver, and make the quiver, then mutate. You should get the same answer. Okay? So just to get some practice, try to do this. Okay? So this will give you practice in doing this construction. So for boundaries, I'm just going to put, if I'm a boundary arc, I'm going to put ones. Okay? So this has to do with coefficients, but I'm just going to use ones. Yeah, so I don't need lengths in this talk, but I just mentioned that because if people were aware of this old, like this really classical Ptolemy relation, then that result is stated in terms of lengths when you put this inside of a circle. But this relation, this exchange relation, you don't need anything to do with lengths. Yeah, it's just a formal relation. Yep. That anytime you have a quadrilateral and two diagonals, you do this. Okay. So good. So draw quiver, then mutate, or flip this diagonal, then draw the quiver. You should get the same answer. Flipping and mutation is the same thing. Okay? So this is just polygons. And in general, if you have an, it's an n plus 3 gon. Okay? This is the picture you have. So I want to generalize this to more general surfaces, not just polygons. Okay? So that's the point of today. So a cluster algebra of surface type is going to be something that comes from a more general surface. Okay? So for some time, I'll have to talk about marked surfaces. Okay. So I'm going to say a bunch of words, and for people who know what they mean, that's great. And for people who don't know what they mean, I'll give you a bunch of examples. Okay? So I'm going to tell you what kind of surface it is. And if these words don't make any sense to you, that's fine. I'll give you a bunch of examples. So S is a connected, oriented Riemann surface. With or without boundary. And the boundary I'll write like this. Partial S. That's the boundary of my surface. And inside this surface, I'm going to have a bunch of marked points. So spectral points on this surface that I'm going to call marked points. So this is going to be the set of marked points. So this is a finite set. And for some technical reason, I want there to be at least one marked point on each boundary component. At least one marked point on each boundary component. Okay, and these two bits of information together, I'm going to call marked surface. Okay? So a pair of a surface with a finite set of marked points is going to be called a marked surface. So I'll show you all of the examples I'm going to consider. Okay? So everything I'm going to consider has some genus, has some collection of boundary components, has some punctures, and and some marked points on the boundary. So here's a bunch of examples. Okay? So here's a genus 0 example. So I'll have a sphere. Okay? So I mean like not projective space or something like this. Okay? Not something that's, not an oriented manifold. So, or Klein bottle or something like that, okay? So here's something of genus 0 with 4 punctures. So I'm going to write G equals 0 for the genus, okay? And B is going to be the number of boundary components. This one has none. P is the number of punctures. So these points that are not on a boundary component, so there are 4. And C is the number of marked points on a boundary component. So there are 0 here. Okay, so I'm going to draw a lot of them so you remember what these G, P, B, and C mean. Okay, so here's another genus 0 example. It's an annulus. So this is a disk with a disk cut out. Okay, so this is empty here. Okay. So this is genus 0. It has 2 boundary components, this one and this one. Okay. It has all of its marked points are on a boundary component, so it has 0 punctures. Okay. And the number of marked points on boundary components is 3. Okay. So I'll draw 2 more examples. So here's a torus. Okay. And I can... any question? Okay. I thought I heard a question. Okay. And I can cut out a disk. Okay. So let me just add some punctures. All right, so let's write down all this data. So genus is 1. Boundary components, there's 1. Okay. There are 3 punctures. And there's 1 mark point on a boundary component. And last example. So genus is sort of the number of handles the thing has. The number of holes in the donut. Okay. So this one has genus 2. Okay, because there are 2 of these. So let me add a puncture just to make a count. And I'm cutting out this disk. Okay. So genus is 2. There's 1 boundary component. There are 2 punctures. And there are 3 mark points on boundary components. Okay, so these are the sorts of surfaces I'm looking at. They're characterized by this data. I don't know. Yeah, it's an annulus. It's an annulus. Yeah. So yeah, you asked what this is. Okay. So yeah, it's an annulus or like a cylinder. Yeah, it has 2 boundary components. Yeah. Yeah. So it's a disk with a disk cut out of the middle. Okay. Any questions? Further questions? Okay. So I want to start triangulating these types of things. Okay, so I want to add arcs that connect these marked points and then make triangles. Okay, make a triangulation. But I want to exclude some examples. So I have to exclude the following things. So I want to exclude spheres with 1 puncture, 2 punctures, or 3 punctures. So that's the minimal sort of example in terms of number of punctures for my sphere. I want to exclude monogons with 1 puncture or 0 punctures. So monogon just means this. Okay, it's a one-sided thing. All right. And I want to exclude bigons, 2-sided things, and triangles with no punctures in the middle. Okay, so a bigon with no punctures would be this. It's a 2-sided thing with no punctures inside. And a triangle is a 3-sided thing with no punctures inside. Okay, so I want to exclude these. So now I'll tell you what I mean by arc. So the whole point is to generalize this. Okay. This thing keeps slipping. Let me try to fix this. Okay, let's see how long I go. All right, so Good. Arc. So arcs are going to be the things that replace diagonals in the picture that I erased. Okay? So an arc gamma inside a marked surface is a curve in the surface up to isotopy. So I'll tell you what this means. It just means moving around the curve inside my surface. Okay? So I'll mention this in a second. Such that some things need to be satisfied. So I want the endpoints of my arc to only lie on these mark points. Okay? So an arc just can't start anywhere. It has to start at a mark point. All right? Yeah? I think I don't want to cross the thing. I don't want something to cross itself. I can't hear you. Sorry. So what's the difference? Transform an arc to okay, so I mean isotopy. Okay. Yep, isotopy. So I mean, okay, so I mean if I have something like this, I mean for me it's the same as this, okay? But also what you said, okay? But this is all I'm going to use in my talk. So gamma is disjoint from the collection of marked points and the boundary of the surface, except for at its endpoints. So I don't want my arcs to hit other marked points except where they started in, okay? And C, an arc doesn't cut out an unpunctured monogon or an unpunctured bigon. So I don't cut out these things with my arcs. And D, I don't want my arcs to cross themselves. Okay? So gamma doesn't cross itself, except possibly at the endpoints. Okay? The C part. So I don't want, if my surface, if I have something like this, I don't want it to look like that. Okay? But if I have a boundary component cut out, then it's okay. But well, this is homotopic to the boundary, but if I have something like this, okay? Yeah, so I don't want this to just cut out something without punctures, but if I have punctures or something like that inside, it's okay. So now that we know what arc is, I want to say what a triangulation is. So just like a triangulation of these polygons, it's a bunch of diagonals that don't cross each other. Okay? But now I'm allowed to isotope things around, so I don't want to cross each other up to isotopy. Okay? So I want to find representatives that don't cross each other. So triangulations And I promise you I'll do a bunch of examples soon. Okay, just have to get set up. Two arcs, gamma and gamma prime, are called compatible if this quantity that I'll define in 1 second is 0. So this quantity says, so what is this? It's the minimum over all the crossings, so it's the minimum of the number of crossings up to isotopy, okay? So it's the minimum of the number of crossings of alpha and alpha prime, as alpha and alpha prime range over all of the arcs that are, all of the curves that are isotopic to these, okay? Such that alpha is isotopic to gamma, and alpha prime is isotopic to gamma prime. Okay, so for example, here's what I mean. So say I have 3 marked points on a disk, okay? And I have this arc, and I have this arc. So are these compatible or not? So they're compatible because I can pull this one away from this one so that they don't cross. Okay? This is what I mean. So if you can isotope them so that there's no crossing, then we call it compatible. Okay? So isotopy I can get something like this. Okay? So these arcs are compatible. But for example, these I can't, right? Okay. All right. So now a triangulation is just going to be a maximal collection of pairwise compatible arcs. Okay? So I want to add in as many arcs as I can so that they don't cross up to isotopy. Okay, so definition. An ideal triangulation is a maximal collection of pairwise compatible arcs. So it's a collection where every pair of them is compatible. Yeah? Uh-huh. Okay, so I didn't write this. I pulled this from various references, and they all say up to isotopy. So I don't know. Yeah. So I want that to be a different triangulation. I mean, as long as I have 2 marked points. So if I have 2 marked points and I wrap around and I end on a marked point, then that's a different triangulation than just going straight. As long as if I have two arcs. I mean, it's not a triangulation. I need more than one arc. Yeah. I mean, if I just have two marked points in an arc, it's not a triangulation. I need two arcs in that case. Okay, so let me give you a bunch of examples. So I want to tell you about these examples that I told you in the first lecture, right? The two-chronoker and the Markov quiver and the dreaded Torus. Okay, so let me show you how these come from surfaces. Okay, so this two-chronoker is going to be an annulus. So I take a disk and I punch out this disk, okay? And I want to have at least one marked point on every boundary component. So let's triangulate this thing. So as I was just saying, I need two arcs to triangulate this, okay? So these two arcs will triangulate this. So it takes some work to see that now I've split this thing into triangles. Okay? Maybe it's not easy to see when you just start, right? So like if I try to see a triangle, like I can see this. So here's a side, here's a side, here's a side. Okay? So in any case, I split all of this picture into triangles. Okay? So in a second, I'll give you a proposition that tells you how many arcs you need to triangulate a surface in terms of this data, this genus, boundary component, and punctures, and so on. Okay? So that it'll help you when you just start, like, to know how many arcs there are. So this is going to be the two-chronoker, and right now, I haven't told you how to associate a quiver in this more general case. I've only told you for polygons. Okay? But soon I'll tell you how to associate a quiver to this picture, and you'll actually see the two-chronoker. Yeah, so I have a disk, and I'm cutting a disk out. Two boundary components, each of which have a marked point. Yes? Yeah? Uh-huh. Right, so a triangle can be gotten by using this edge, and this edge. Okay? And internally, so I can use this edge, this one, and that one. Okay, so you just look for things with three sides. Okay, it's hard to see. It's not the triangle that you're used to seeing, right? But you look for things with three sides. Those sides can be a boundary edge, or they can be an internal arc. Okay? Sorry. Can somebody tell me what? I can't hear you. Delta complex? Oh, this is what you asked? I think it's just it's a triangulation. Yeah. So I mean, these are really triangles. Yeah. Okay. So is this okay? Why this is a triangulated? Okay. Yeah. These two are isotopic because you want to rotate this. I don't think you can. That's an action of the mapping class group. That's a Dane twist, right? But I don't want to do that. Yeah, I don't want to do that because that's like acting by a Dane twist, right? But I don't want to do that. Okay. boundary. So I just want to write this so because people asked me the question. Okay. All right. So Markov quiver is going to come from the surface that is a torus with a single puncture. Okay? So it's going to be a torus with a single puncture. And no boundary components. So I'll draw a triangulation of this thing, and then I'll come back to these pictures when I want to draw the quivers in a bit. Okay? So I need a lot of colors. So here's one arc. Okay? So it goes around the back of the thing and comes back. Okay? Here's another arc. It starts, so I have to start and end my mark points here, my arcs here at this puncture. Okay? Remember, they can't start and end anywhere. They have to start and end at a mark point. So here's another one. Okay? And if you look at this, I haven't yet triangulated the surface. Okay? I don't have triangles, I have quadrilaterals. Okay? So let me draw one more. So I'm going to again start here and end here, but I'm going to take sort of this strip around and this strip around. Okay? So let's try to do this. So I'll come around. So I'm coming around the front of the thing, and then I'll go behind. Okay? So I'll leave, I'll go behind. Here, I'm traveling behind the thing. And then I re-emerge in the front, and then come back. Okay? So this is another arc. And for those of you who have taken some topology course, you know that you can get the torus from a square by identifying these sides and these sides, opposite sides. Okay, so maybe I'll draw this picture. So this red curve, so these two are identified to get this red circle. Okay. And these two opposite sides are identified to get this blue circle. So what I mean here, if you haven't seen this before, is if I take a sheet of paper and I identify these two, and then identify these two, I get a donut. Okay, so if I glue these two, then glue these two, I get a donut. Okay? So the colors mean what I'm gluing together. And this yellow one should look like this. Okay, in this picture. All right, so one more example. So this is this dreaded torus. So maybe I will try to draw it here so that I don't take, because I'm going to leave this up, I don't want to take all the board space. Okay? So dreaded torus. So this dreaded torus is going to be a torus with one boundary component with a single mark point on it. Okay? So it's going to be a torus with one boundary component. And this one boundary component has a single mark point. Remember, each boundary component has to have a mark point on it. Okay? So if I draw it as a torus, it's a donut where I've punched out a disk and put a mark point on it. But to triangulate it, I'm going to draw a picture like this. Okay? So let's do that. So for a torus, I start with a square. I identify opposite sides. Okay? And now let me draw this disk that I'm punching out. So I'm punching out this disk, and it has a single mark point on it. Oops. Here. Okay? So let me try to write down a triangulation of this. And I need maybe even more colors. So if I have this arc, and so now I have a triangle here, but I need one more arc, okay, to make a triangle, to make a triangulation. And this is the one I need. Okay, so this is a bunch of examples I'm going to come back to in a moment. So I want to tell you a proposition. If this is tough for you to see whether you have a triangulation or not, let me tell you the number of arcs that you have so that you can guarantee that you have a triangulation. Okay? So here's a proposition. So the number of arcs in an ideal triangulation of a marked surface so I'll call this number n. So the number n of arcs in an ideal triangulation is given by this formula. So these letters are the same as I used here. So genus, number of boundary components, number of punctures, number of mark points on boundary components. Okay? So it's 6 times the genus, plus 3 times the number of boundary components, plus 3 times the number of punctures, plus the number of mark points on boundary components, minus 6. Okay? So if you try to prove this, this comes from looking at the Euler characteristic. Okay? So at least when you do these examples, you can tell if you're done. All right? This tells you how many arcs you need. Okay. So far I've told you about triangulations, but I haven't told you about 2 other things that I need to make cluster algebras, right? So if you remember the picture that I started with, I had a triangulation and I was flipping things, right? So to flip, like flipping corresponds to mutation, okay? So I need to tell you how to flip things. And it's the same thing as it was in that picture. It's just harder to see, right? You look for a quadrilateral that includes your arc, and then you replace it with the only other arc that you can, okay? And I need to tell you how to get a quiver from one of these triangulations, okay? All right, so let's first tell you about flips. So I have until 20 minutes, right? Okay. So ideal triangulations, I have to speed up a little bit. Are connected by sequences of flips. Okay. So maybe I won't define a flip to save time, but it's exactly what I said out loud. Okay? So if I have an arc, if I have any arc inside of a triangulation, and I look at the quadrilateral that it's inside, and I replace it with the only other arc that I can. Okay? That's what a flip is. So maybe I'll show you an example rather than define it. So let's look at this example 1. Say I try to flip this. Okay, so you've already seen examples in the polygon. This is what I started the lecture with. But in this case, if I want to flip this, so example 1 again. So here's example 1. I have these two arcs. And say I want to flip this one on the left. Okay. There should be a unique arc that I can replace this with so that I remain a triangulation. Okay? And here's what it is. So I still have this one. Nothing happens to him. Okay. And this one, when I flip it, what I get is this arc. Okay? This takes some practice. Right? So stare at it at home. Okay? It's not easy. Sometimes I look at these for like 10, 15 minutes, you know? It's like okay. Great. So I want to tell you about one type of triangle that's kind of poorly behaved that pops up in this business. Okay? And this is called a self-folded triangle. And then after that, I'll tell you how to get the quiver. But it's the same as what I said before. Okay? So self-folded triangles. And once we have a quiver, we know that we can get a cluster algebra. Right? So that's going to be the point. So say that I have a triangle. I mean, so this kind of picture is not allowed, but I have some triangle inside of some triangulation. Okay? This is what I mean here. Okay? And a self-folded triangle is going to mean I take this triangle and I stretch it and then glue this edge onto itself. Okay? So what I mean is I stretch it like this and glue it together. So the picture that I get looks like this. Okay? So do you see this? You take this, you glue it on itself, and this edge that's glued to this edge becomes this one. Okay? So this is called a self-folded triangle. And these can pop up in triangulations. They pop up when you have punctures, like this. Right? When you have punctures, you can have these self-folded triangles. Okay? And in all of this theory, these things are the problem all the time. Okay? And just some terminology, I'm going to call this a radius of my self-folded triangle. And I'll call this the loop of my self-folded triangle. Okay? So here's an example of flipping one of the arcs inside of here. Just to give you another example of flipping. So say I have this self-folded triangle, okay, this one. And say I'll call this loop gamma. All right? So if I want to flip gamma, I replace it with the only other arc that I can to remain a triangulation. And I get this one. Okay? So I should mention, like I said, these things are very badly behaved, these self-folded triangles. And the point is that if I try, so I flipped at this loop, and I got this. But I cannot flip at the radius. There's no way to flip at this radius. Okay? And I won't talk about this, but in this paper by Fomin-Shapiro and Thurston, where all this comes from, they have to use something called tagged triangulations. They have to decorate these arcs with something called tags to allow you to flip at these things. Okay? but I won't talk about it. Yeah, it's not relevant, I think. I mean, yeah. Yeah, I'm certain, I don't know. Yeah, yeah. Okay. So in the last 15 minutes, I'll tell you how to get quivers from triangulations. I'll go back and I'll get quivers in these examples, and then I'll tell you the theorem about where algebras are, and so you can have the cluster algebra, right? Yeah. What's that? I don't know. Yeah, does anybody know why you need oriented surfaces? Yeah. Yeah, exactly. Yeah, you're absolutely right. You have to know what clockwise means, right? Yeah, absolutely. Yeah. Okay, so you do need orientable. Okay, so quivers from triangulations. Okay, so if I have a triangulation of a surface, so a triangulation is made up of a bunch of arcs which are pairwise compatible. Okay, maximal collection that's pairwise compatible. So say I have a triangulation of some surface. Then to that, I'm going to associate a quiver without loops and without two cycles. Okay, so my quiver is going to have vertices 1 through n, 1 for each of these arcs. Okay? And the arcs, okay, but I guess these are the mutable ones, right? So I'm going to have a mutable one for every arc, and I'm going to have a frozen one for every boundary component. Okay? So I'm just talking about the mutable ones right now. So for a vertex I, I'm going to associate an arc gamma I. And for the arrows, well, let me explain. So I'm going to explain this. But the point is that it's exactly the same as the polygon story, except if you have one of these self-folded triangles. Okay? So you move clockwise, you make a cycle clockwise. But when you have these self-folded triangles, it's a little bit more painful. Okay? So let me write. I'm running out of board space now. So I think, yeah, I only have 10 minutes. So I might just tell you where to read about the self-folded triangles, and I'll just tell you that you go around in cycles, because I want to get to the cluster algebras theorem. Okay? So for any triangle, in your triangulation, which is not self-folded, you get an arrow from I to j when gamma I and gamma j are sides of your triangle that's not self-folded, with gamma j coming after gamma I clockwise. Okay? So same thing from before. With gamma j following gamma I clockwise. Okay? And then B and C tell you what happens. I mean, so you only get, for these triangles, you only get arrows for non-self-folded triangles, but you may share edges with these self-folded triangles, so B and C tell you what to do. Okay, so you get arrows when you share edges with self-folded triangles. Okay, so these are things to do with self-folded triangles. And I'll tell you where to read this. So the original work on cluster algebras from surfaces is a paper by Fomin-Shapiro and Thurston from 2008. Okay, so everything is in there. And there are some great notes by Ralph Schiffler as well, like some expository lecture notes. So also notes by Ralph Schiffler. So you do these, and then you may have created 2 cycles, so you remove them. So instead of stating this, let me show you in these examples. Okay. So I'll go back here, and I'll get a quiver. Okay, and I've told you the answer. It should be the 2 Kronecker, which is the one that has 2 vertices and 2 arrows, okay, pointing in the same direction. And I'm going to get a bunch of frozens, but if you ignore the frozens, you get the 2 Kronecker that I gave you in the first lecture. Okay? So here I go. So I should have a vertex at every arc that's not a boundary arc. Okay? So there are 2 such ones. So I have 2 vertices that are mutable. And then I have a frozen for every boundary edge. So here's a boundary edge. I'll have a frozen. Okay? And here's a boundary edge. This one. I have a frozen. Now I go through and I write down my clockwise cycles. Okay? So let's do this. And I'll just use red color just so that you can see. All right? So I'll call this 1, this 2, I'll call this vertex 3, and this vertex 4. So I'll use red color to draw my arrows. So here's a triangle. So this one, and this one. It's 3 edges, 3 sides. So this side, and this side. So now I want to make an oriented cycle here, and I'll go clockwise. Okay? So I'm going to connect this one to this one, here to here, and here to here. Okay? So I've done this one time. And now I have one more triangle. That's the outside. Okay? So 1, 2, 3. Okay? So that's another triangle. So I need to make a cycle here. All right? So here's how you do it. So I need to move clockwise. Okay? So I can go from 4 to 1 clockwise. Okay? And then from 1 to 2 clockwise, and then 2 back to 4. Okay? So let me just draw the picture. Here's 1, here's 2, here's 3, here's 4, and then I have 2 arrows from 1 to 2. 1 is here, and 1 is here. Okay? So I have 2 arrows from 1 to 2, so there's my 2 Kronecker. And then these other arrows I get look like this. Right? So now I have the 2 Kronecker quiver, so I can get a cluster algebra. Okay. So now I'll draw this one as well. So here I only have 1 vertex, okay? So these are identified, okay, in this 1 vertex. These are all the same vertex, okay? But now in my quiver, I want a vertex for every arc, okay? So I want a vertex for the red, for the blue, and the yellow, okay? So let's do this. And I don't have any boundary components, so all of my vertices will be mutable, okay? None of which will be frozen. So now I'll draw it in white just to have a different color, okay? So I'll call this vertex 1, and this one's the same one, right? So this is also 1, because I'm gluing these together. Okay, and I'll call this one 2, and this one is also 2, because I'm gluing these together. And then I'll call this one 3. Now I move around, and I make clockwise cycles. Okay? So here's one. And here's another one. Okay, so I'm supposed to get the Markov quiver, which is the quiver that has 3 vertices and 2 arrows, 2 arrows, and 2 arrows. Okay? So if you take this picture, you get that, in fact. So from 1 to 3, I have 2 arrows. One here, one here. And the same thing is true in all the other cases. Okay, so from 3 to 2, I have 2 such arrows. And from 2 to 1, I also have 2 arrows. So this is this Markov. So because I only have 2 or 3 minutes, I won't do this one. Okay, so I'll leave this as an exercise. But you get exactly this quiver, this dreaded Torus that I got from the first lecture. So you can try to do this on your own. So try to draw the quiver. This is an exercise. And talk to me about it. Okay? You get the dreaded Torus. And I think I've done it in such a case that you have exactly one boundary component. So you'll have one frozen vertex. So it's exactly the quiver that I drew in the first lecture has one frozen vertex. You'll get the exact same quiver. Okay? Okay. So now I'll write down the final theorem. So here's a definition. So, okay, if you have a triangulation of one of these marked surfaces, you can produce a quiver. And from this quiver, we've already seen how to produce a cluster algebra. Okay? So if your quiver comes from some triangulation like this, I call this cluster algebra surface type. Okay? So if I have a quiver from a triangulation with some x1 through xn on those arcs, this is called the cluster algebra associated to my surface. And that cluster algebra would be called of surface type. The marked surface. Sm. Okay, so now I'll write the last theorem, which we already said implicitly. Okay, so here's the theorem of Fomin, Shapiro, and Thurston. In 2008, it says that there are bijections between the cluster variables in a cluster algebra. So this cluster algebra comes from a surface, okay? And the arcs of the marked surface. So these are the arcs occurring in any triangulation, okay? Okay, so I'll just finish the sentence. So x gamma, gamma. Okay, and the clusters are in bijection with triangulations. So this picture I drew for the polygon is really, I mean, the example you should keep in mind in all this, okay? But I've given you more. And the last thing I want to say is that, I mean, mutation of these quivers corresponds to flipping arcs. But I'm not allowed to flip the radius of a self-folded triangle yet. Okay? So if I would have had time to introduce these tag triangulations, then I could add one more sentence that says mutation and flips coincide. Okay? But right now, they only coincide if I don't flip at the radius of a self-folded triangle. Okay, so I'll talk about these surface ones are very much most of the ones that are finite mutation type. Okay, and they have the nice property that if you there are not many cluster algebras, types of cluster algebras that if you mutate, you stay within the same class. Okay, so meaning if you mutate a quiver from a surface, you still remain a quiver from a surface because it corresponds to flipping a diagonal. This is why they're so special. And they're special for a lot of other reasons too. Okay, thanks. Okay. Yep, sounds good.